even if we're constructing it from the bottom up, there's different representations. And in fact, Weinberg likes a square root version of parameterizing the coset. Maybe he's the only person. He has very good reasons for being allowed to stick with his original results rather than the exponential representation, which everyone else seems to favor, including me. So if we go back to talking about QCD, then it's common to call this curly V f over root 2. F is a decay constant. And so the conventions then are the following, at least one possible choice of conventions. There's some choice about where you put the 2's, and then everything else is fixed. So this is one possible common choice for the exponential representation. And then that gives you the Chiral Lagrangian. It looks like that. And if you expand this out, you get the standard kinetic term for the pi field. That's what this normalization factor does. And then if you keep expanding, you get some interaction terms, like this one, etc. So there's 4-point interactions in that Lagrangian as well. And that's because we had a curved, our coset is non-trivial. So part of the story here has to be, when you talk about symmetry breaking, has to be about the fact that symmetry is also broken explicitly in the standard model. And so you have to add, the goldstones are only pseudo-goldstones. You have to add a mass. And the way you do that is by doing a spurion analysis. Remind you how that goes. You write out the mass term like this into left and right. The mass, you could say, is just a diagonal matrix of up and down for SU2. And you could pretend, rather than talking about things that are violating the symmetry, like these guys, you let the mass transform and pretend that you actually have something that's invariant. By pretending that the mass transforms, you're able, if you pretend the mass transforms in the chiral theory, of constructing things that violate the symmetry in the same way. You construct invariants in both theories with this kind of transformation law. And then when you go back and fix M and say, no, it doesn't transform, it's really a fixed thing, not a field that could transform, it's fixed, the number, then you violate the symmetry explicitly in the same way as up here. It's a trick for how to build things that are covariant in a certain form. So you could add the invariant operators of the Chiral Lagrangian. This is a different V, some parameter, different V than this curly one we were talking about earlier, which is now called F. Okay, so this is the spurion story, how to break symmetry explicitly in a different theory, the same way. And if you expand to quadratic order, you get mass terms for the pions. I won't go through that. But one kind of important thing about it is that the the mass proportional to V times the quark mass, so V0. So the parameter in the Lagrangian, linear in the quark masses, quadratic in the Goldstone mass. You can also couple currents, and you can do a similar type of analysis with spray-on type transformation analysis for the currents. And I'm not going to go through this in any gory detail, but just enough to do what we need to do here. So here's a left-handed fermion current in the standard model. Could be coupling to the W boson, for example. And you could think of getting J by taking a derivative with respect to functional derivative with respect to a field that's left-handed. And then I can do the same kind of thing where I think about this L and let it transform, just like I was letting the M transform. So think about there being L, J is this capital J times minus L. And if I then think about this L mu transforming, I can build a Chiral Lagrangian and then use this formula to construct the current in the Chiral Lagrangian. So you couple a spray-on current. So L mu, some L mu A tau A. And you, in this case, in order to couple it, you can let it transform like a left-handed gauge field. And then you get something that's invariant. So the transformation that'll make something make it invariant is to think of it as a left-handed gauge field. So L mu goes to L mu, L dagger, and then that gives you an invariant in the original theory. And then you build an invariant in the PX theory. And so if you do this, then you're replacing in your Chiral Lagrangian your partial derivative by a covariant one, and it acts on the left, because that's where the sigma is transforming. And so it's an easy way of building that in. And you just get an IL times the sigma on the left. So you take everywhere you have a derivative, you replace it by this combination. So we had two derivatives in our Chiral Lagrangian, expand it out, and we can figure out how to put in a left-handed spray-on. Okay, so the spray-on is kind of a general way of going from one to the other just by tracking symmetry breaking. And you'll get some more practice with some of this on your problem set. So on your problem set, what I've asked you to do on problem set 2 is to do a one-loop calculation in this Chiral theory. So you can really see that this is a quantum field theory, an effective field theory, not only a tree-level mnemonic theory, but really a field theory in its own right, where you have to consider loops, contractions, Wick's theorem, everything is the same as a real quantum field theory should be. It's an effective field theory of certain degrees of freedom. So you do a one-loop calculation for the decay constant. And that's basically, there's two problems in the problem set. The first one is fairly straightforward. And then that's the second problem. That's all I'm asking you to do because it's fairly involved. It's like maybe two normal problems. Okay, so here's our Chiral Lagrangian. And we're going to count in this Chiral Lagrangian in terms of power counting, partial squared as being order V0 MQ. That means we're going to count p squared as being order m pi squared. That's going to be our counting. And so we're going to expand in these things as small and something else that is large. And we'll figure out what the large thing is in a minute. So we do the expansion like that, where something is downstairs that has mass dimensions, and the things that are upstairs are p squared and m pi squared. So the type of expansion we have here is a combination of a derivative expansion, although it's a bit of a different derivative expansion than before, and an MQ expansion. Simultaneously, we have an expansion in these two things. If we look at L0, then it has things in it like a propagator, dashed line for the scalar pion propagator. It has 4-point interactions. And if you look at how those scale, we could write out what the Feynman rule is, but if you look at how they scale, they go like p squared over f squared, or m pi squared over f squared. So the p squareds you can put on shell, it would be m pi squared over f squared. And you will actually need this Lagrangian and this Feynman rule for your homework, so let me tell you what it is. And I'll leave it to you to work out the Feynman rule. These are commutators. There's a factor of 6. And then further. And then there's also a term that would give 4-point scattering from the MQ term in the Lagrangian. So that also gives an m pi squared over f squared term. And that looks like that. Okay, so you could build up higher point functions, 6-point function, et cetera, from the leading order Lagrangian. It has all this in it. It has 2 parameters, f and v0. Okay, so what about loops? And what about this? What is this scale lambda chi? So the type of loops that you can have if you have a 4-point interaction, and just draw a solid line since it's easier than drawing dashed lines. Think of all these as dashed. So there's cross diagrams as well as the original diagram. This is not the calculation I'm asking you to do in the homework. If we thought about our example of pi plus pi 0 scattering, then we could contract up pi plus and pi 0 fields, and we could have a loop that looks like that. And in order for our theory to be unitary, we have to think that these loops make sense, because there's cutting rules, and all that story should go over for this quantum field theory, and it does. And that means that, if you like, the imaginary part of this loop is needed, and you can't get the imaginary part without the real part, so we have to also think that the real part is a physically meaningful thing. And so we can go ahead and compute it and figure out what's going on. So there's derivative couplings that go like f squared, 1 over p squared over f squared. L is the loop momenta. Primes are the final. Unprimes are the initial. You can parameterize it however you like. I'm using here dimensional regularization. I like dimensional regularization, and so do you. Dimensional regularization here preserves Chiral symmetry, which is something that we want to preserve. I'll tell you a little later what would have happened if we'd done this with a cutoff. So if you do this calculation, just calculate those guys. You get terms that go like p to the fourth. You get terms that go like p squared m pi squared. Terms that go like m pi to the fourth. You get a 4 pi because it's a loop. And then you get an f to the fourth because there's 4 factors of f. So what this behaves like is p squared or m pi squared over f squared, which was our tree level 4-point function, times something that's causing suppression, which is p squared or m pi squared over 4 pi f squared. So the loop is actually down by a factor of p squared over 4 pi f all squared. So just by explicit calculation and not breaking the symmetry, we see that loops are suppressed by p squared over lambda chi squared, where lambda chi here is defined to be 4 pi f. So the 4 pi is important because f is like 130 GeV, and you need this 4 pi in order to make it a viable, in order to have some range for your Chiral expansion. So if you plug in numbers, depending on your conventions for f, and there's a couple of common conventions, you can get numbers that are like 1.6 or 1.2 GeV, so some scale of order of GeV. On general grounds, you could also ask the question, well, if I just think about it from the effective theory, what is a reasonable scale for the denominator, for this lambda chi? Remember, you're going to have to construct higher order operators as well, and so you need to kind of figure out what's the right scale for the suppression of those higher order operators. And if you did it on physical grounds, then what you'd expect the lambda chi to be is about the mass of the row, because that's the lowest energy hadron that you've left out of this Chiral theory. So you might expect lambda chi is of order m rho, which is sort of 770 MeV. And so you can't really say whether it's 770 or 1.2, because the difference between those are, although important numerically, is not kind of within the realm of the kind of factor 2-ish meaning of these twiddle symbols, right? So these twiddle symbols mean parametrically of order. Then there's two symbols. There's much greater, much greater than, or twiddle. Twiddle means factor of 2-ish. Much greater means parametrically of order, much less than. And just with those two symbols, there's some freedom. These different ways of doing an estimate for what lambda chi are, just saying that there is that freedom, and you have to do the full calculation in a particular channel to really figure out for a particular piece of phenomenology what the lambda chi is. Extract it from data if you like. Okay, so that is likely a good place to stop. And next time we'll talk a little bit more about these loops. And we'll talk about what happens to these loops in the power counting theorem that you have that organizes all diagrams in this theory and tells you what you have to do if you want to construct the Lagrangian order by order, how you deal with when to put in the loops, when to put in the counter terms. We'll talk about those things next time.